Thing that we've already talked about, which is the binary system. So I'm going to show you how the binary system works, and then once we've gotten through that, I will show you actually a second numeric system called hexadecimal, which makes it very easy for us to discuss large binary values. So before we actually get to those particular topics, let's start with what we're all familiar with, which is the decimal counting system. So in the decimal system, we have 10 digits, 0 through 9. And what that means is that once we get to numbers that are larger than 9, we have to use a second digit to represent them. So once I get to 10, for example, I have to add a second digit called the tens place, and then I can now represent digits that are larger than 9. In fact, I can go up to 99 in that particular case. But once I go above 99, I again have to add another digit called the hundreds place, right? And this continues, etc., etc. We can represent any digit that any number that we want under this particular scheme. So, this diagram kind of shows how it works. The ones place is equivalent to some value times 10 to the 0. The tens place is equivalent to some value times 10 to the first. The hundreds place is equivalent to some value times 10 to the second, and then times 10 to the third, etc., 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 until we have enough digits to represent the number that we're looking for. All numbering systems work this way. All of them do. The only difference between this numbering system and the numbering systems that we're about to talk about are the value of this base, the base part of the exponent. So the decimal system is a base 10 numbering system. The binary system that we're about to discuss is a base 2 numbering system. So we can recreate this diagram using base 2 numbers, and we'll do a little bit of that as we go through today. So let's take a look at the binary system. Here you can see on the very right-hand side we have decimal values, the decimal numbers, right? And then we have those numbers represented using binary over here in the leftmost columns. And so you can see that binary, we're restricted to only 2 digits, 0 and 1. Right? That represents the voltages that we discussed in previous videos and in class, where something can either be on or off. Right? With that in mind, when I want to count to values that are larger than 1, I have to start adding additional digits. So here I can do 0 and 1 with just one digit. If I want to go larger than 1, I have to add a second digit. And then once that's done, right? So this digit then represents the 2's place. The first digit is the 1's place. This digit is the 2's place. That gives me 2 additional digits that I can represent. And then once I have gone past those, once I want to count higher than 3, I then have to start including additional digits. So every power of 2 then, I have to use an additional digit to represent that, start representing those particular values. This is exactly the same as the decimal system that we just saw, that we're already familiar with. The only difference is that we're using a base of 2 to represent these values instead of a base of 10. Now the numbers that you see up here on the screen, especially these 4-bit binary numbers, are very, very useful, very, very important. And so I would highly recommend that you take the time to go ahead and memorize those particular values and get them so that you don't have to think about how to convert back and forth. You can just automatically come up with those values. It'll take some time, but it's going to be very useful for you to have these numbers readily available, to have these numbers memorized, for reasons that will become clear a little bit later on in this video. So now that we understand a little bit better how the binary system works, right, let's talk about groups of bits. So a bit is one particular digit, right? We see we've got one particular digit here, and then once I go above 1, I add a second digit, right? So now I have 2 bits here. So it's common to use bits in groupings, since one bit by itself does not convey a whole lot of information, right? So the most common grouping that you're likely to see is called a byte. A byte is a group of 8 bits. In fact, I imagine that most of you are already familiar with groupings of bytes, especially the larger values of bytes, such as kilobytes, megabytes, gigabytes, terabytes, etc. These are often used to represent the sizes of various things within a system. Files, for example. Another less common but also very useful grouping of bits is called a nibble. A nibble is half the size of a byte, so a nibble is only 4 bits. That by itself is not used within the computer particularly often, but it is very much useful for humans when talking about large binary values for reasons that we're about to see on the next slide. And so then the final grouping of bit is called a word, and a word might be the most important grouping of bits on a particular system. A word has no defined size. The size of a word depends on the particular computer that you're talking about. So, when I started learning about computers back in the early 2000s, the word size was 32 bits, and all computers basically were 32-bit computers. And then, several years ago, they started switching everything over so that now, these days, you can't buy 32-bit computers anymore. You can only buy 64-bit computers. So 64 is now the most common word size that is in use in the world today. And what the word actually represents is the amount of data that's being operated on at one time within a processor. So if I ask a processor to do something, if I give it an instruction, I tell it to perform some particular operation, the amount of data that that operation is going to act on will be a word, right? So if I'm adding two numbers together in a processor, I'm actually adding two words together. I'm actually adding two 64-bit values together in a particular processor. So it's a very important value, and it's good to know what the word size is of any particular computer that you're using. Okay, so now that we've got some binary experience, I want to talk to you about the second numeric system that's going to be useful for us in this course, which is hexadecimal. So here you can see hex represents 6 and decimal represents 10. So hexadecimal means 16. Right, base 16, and just like we saw with decimal and binary, it behaves in exactly the same way, except for the base of that exponent is now going to be 16 instead of 10 or 2, which means we need 16 different digits. Now we only really have 9 digits to use, so to get those extra digits, we start using letters of the alphabet instead. So you can see here the letters of the alphabet down at the bottom to represent the larger values within the hexadecimal system, where A represents 10, B represents 11, C represents 12, etc., etc. Right? The reason that hexadecimal is so useful, you can actually see kind of on this chart, is that it converts, each hexadecimal value can be used to represent 4 particular binary digits, or a nibble, as we talked about on the previous slide. So those binary values that I said that you should probably memorize, you can see them right here on this particular slide. And eventually you're going to want to memorize the conversions from binary to hexadecimal as well. So it'll make it very easy for you to quickly understand large binary values. So that is really the primary reason why we bother with hexadecimal at all, is because it makes it very easy for us to talk about very large binary values. Even a byte that's 8 bits long, that's 8 different digits, we can represent with only 2 hexadecimal digits. So we've shrunk the size of that value down. The representation, right? The value is the same. We can just use fewer digits to represent it. So looking at hexadecimal values is a lot easier for us as humans than looking at a wall full of 1s and 0s and trying to interpret that particular data. So in a little bit, we'll actually get some practice converting things from binary to hexadecimal and vice versa. But before we do that, I want to try and do some different types of conversions. Let's try and convert some decimal values to binary and vice versa, and then we'll go back to hexadecimal. So the first thing that we see here is the number 89 in decimal, and I want to convert that to binary. Now when converting from decimal to binary, the first thing that you want to do is find the largest power of 2 that fits in the decimal value that you're trying to convert. So in this particular case, right, 89, the first power of 2 is 1, the second power of 2 is 2, then 4, 8, 16, 32, 64, and then the next one after 64 is 128. So 128 does not go into 89, right? That's too big. So 64 is the largest power of 2 that can fit into 89. So what we're going to do then is go ahead and write down a number 1 to represent the fact that 64 can go into 89. That's going to be the first digit of our binary number. Once we've done that, we'll subtract that number from 89. So 89 minus 64 leaves us with 25. And now we need to find the next largest power of 2 that can fit into the number 25. So starting from 64, the next smallest power of 2 is 32. But that's too big. So we need to represent the fact that 32 is too big. And to do that, we'll say there's a 0 in the 32 place. Right? There's no 32s available in 89. The next smallest power of 2 is 16, which does in fact go into 25. So we'll go ahead and put down another 1 to represent the fact that 16 fits in our particular digit. And then we need to subtract again. In this particular case, 25 minus 16 is 9. Right? So now we have 9 left over, and we need to find the largest power of 2 that can fit into 9. 16 divided by 2 is 8. So 8 does in fact go into 9. We'll put another 1 in our binary number to represent this fact that 8 does go into 9. And then we'll subtract again. 9 minus 8 is 1. And we need to keep continuing down our powers of 2. 8 divided by 2 is 4. 4 does not go into 1, so we'll put a 0 in our binary number. 4 divided by 2 is 2. 2 does not go into 1, so we'll go ahead and put another 0 in. And then finally, 2 divided by 2 is 1. 1 does go into 1, right? And the difference between 1 and 1 is 0, so we are in fact finished. This is the binary number that represents 89 in decimal. In fact, one little trick that I'd like to point out is this very last bit here is sometimes called the odd bit. And there's a good reason for that. Anytime you have an odd number in decimal, this bit will be a 1. If you think about it, it's the only thing that could make a number odd, because all of the other digits are powers of 2, or are even numbers, right? So this is the 2's place, this is the 4's place, this is the 8's place, 16, 32, 64, etc., etc. So in order to represent an odd number in binary, this very last bit will always be 1. If it's an even number, this very last bit will always be 0. So that's a neat little trick to keep in mind as you're performing these kinds of conversions. Right? So that's how we convert things from decimal to binary. Now let's talk about the opposite direction, converting things from binary to decimal. When we converted from decimal to binary, I started with larger powers of 2, and I worked my way down to smaller powers of 2. When I'm converting from binary to decimal, I like to do the opposite. I like to start with the smaller powers of 2 and work my way up to the larger powers of 2. So let me show you what I mean by that. The first bit that I see here is 1. The first bit on the right, that binary value, is 1. And that particular bit represents the 1's place. So I know that there's going to be a 1 in this decimal value that we're trying to construct. The next digit, the one that's just to the left, is a 0. That's in the 2's place, so I know that there is no 2 involved in this number at all. There is a 1 in the next place, however, which represents 4's, so I'm going to add a 4 into this particular value, since there is a 1 in that particular place. In the 8's place, the next bit over, there's a 0, so I don't need to do anything. And then in the 16's place, which is the next spot to the left, there is another 0, so I don't need to add anything for that either. But the final value is a 1. That represents the 16's place, right, or I'm sorry, the 32 place. 1, 2, 4, 8, 16, 32. Yep, 32. So we'll go ahead and add 32 onto our value here. And we see that what we're left with is 32 plus 4 is 36, plus 1 is 37. So our binary value, as shown, represents 37 in decimal.